The real paradox here isn't that the ship survived a massive air raid. It's that the step-by-step engineering that hauled her out of the mud is barely preserved in the record. On September 1st, 1939, this vessel fired one of the opening salvos of the Second World War in Europe, often described as the first shots of the war at sea. She was a weapon of immense historical gravity, yet her final days were spent not in glorious combat, but as a shattered, waterlogged barricade suffocating a critical deep-water port. The ship in question was the German pre-dreadnought battleship Schleswig-Holstein. She was built under the parameters of pre-dreadnought architecture. This naval design philosophy relied on a mixed battery of heavy guns mounted on a comparatively slow and heavily armored hull. The engines were designed for an earlier era of naval warfare, and the ship's aging layout and protection standards left her far less tolerant of modern high-explosive damage than newer battleships. By the middle of the 20th century, this made the vessel hopelessly obsolete and highly vulnerable to modern aircraft. She lacked the speed to evade and the deck armor to repel bombs dropped from high altitude. On December 18, 1944, reported by some accounts as the night of December 18th into December 19th, that vulnerability was permanently exploited. Royal Air Force bombers found the battleship at Gotenhafen and are widely reported to have scored 3 direct bomb hits on her upper decks. The ensuing fires and structural failures overwhelmed her internal damage control systems. The great warship foundered and sank straight down into the harbor mud. However, the depth of the water at rest in Gotenhofen was only about 40 feet. Because of the ship's size and the way she settled, parts of her superstructure and upper decks remained above the surface, creating the illusion that the battleship was still somewhat intact. Below the waterline, she was a dead-weight ruin. The sinking created an immediate strategic problem. The wreck sat across a working harbor at the exact moment the front was collapsing. For the Soviet forces arriving at Gotenhafen, this was not heritage. It was throughput. They needed the deep water berths open for cargo and military supply traffic, and the battleship's carcass was now the plug in the bottle. Clearance had to happen fast, with improvised gear, in a port still shattered by war. The initial Soviet assessment of the wreck revealed a grim engineering reality. The ship was heavily flooded, resting deep in thick harbor silt, and structurally compromised by the 3 bomb strikes. Yet, even with these massive challenges, the upper hull theoretically retained enough integrity to be sealed and pumped dry. Salvage engineers initially calculated that if the bomb breaches could be patched by divers, the remaining compartments might hold enough air to break the grip of the mud. It was a daunting task, but one that standard wartime salvage units were trained to handle. In principle, the operation might have followed a familiar pattern: underwater welding, extensive pumping, and brute mechanical force, though on an enormous scale. Diver teams would have mapped out the jagged edges of the bomb craters, measuring the exact dimensions of the steel required to form watertight patches. The theoretical timeline would depend entirely on how fast those patches could be secured under the freezing water. The bomb damage was only half the equation. The exposed superstructure made her look recoverable, and it was easy to assume mud and flooding were the main enemies. Soviet engineers came in thinking in familiar terms: patch the breaches, mobilize pumps, restore buoyancy, reopen the berth. If the hull had remained a sealed, liftable body, they might have refloated her quickly. But a final alteration had been made to the keel, an internal trap that would turn those neat calculations into fiction. The wreck's sheer mass, roughly 13,000 to 14,000 tons pinned to the harbor floor, was a trap by itself. But the real nightmare was what the charges had done to the hull's continuity. Salvage math depends on a ship behaving like one rigid shape, so lifting forces can spread cleanly through an intact structure. Here, that symmetry was gone by design. On March 21, 1945, the remaining German crew chose to turn an already sunk obstruction into a wreck that could not be handled quickly. They set charges to deny the enemy a usable harbor, not by sinking her deeper. She was already jammed in shallow mud, but by breaking her into an unstable, torn structure that would punish any attempt at rapid clearance. When a hull is intact, a lift at the bow or stern can transmit through the whole length, letting the ship behave like a single rigid beam. After the scuttling charges, that beam was snapped. She wasn't one structure anymore, but a disjointed stack of flooded compartments pinned into silt. With a draft of 26 feet 11 inches even in her original form, She needed real depth to float freely. Now the lower hull was shattered, buried, and open from the bottom up, destroying the very compartment volume that normally traps air and creates buoyancy. The Soviet salvage engineers inherited a brutal physical reality. Thousands of tons of broken steel were not just heavy, but glued down by bottom suction. Fine harbor mud had packed into the keel ruptures and hardened the wreck into the seabed like poured concrete. Any attempt to sling cables and pull from the surface risked slicing into the weakened structure. Hidden cracks, distorted joints, and blast-stressed seams could fail without warning, collapsing what remained above. Diver teams had to trace the jagged blast zones by touch in zero visibility, plates bent inward where bombs struck from above, and sections blown outward where the scuttling charges tore from within. The damage vectors didn't just punch holes, they rearranged the ship's interior into a collapsing maze of steel and silt. In that geometry, the old playbook failed fast. Any air or gas you tried to introduce would simply bleed out through unseen vents ripped along the bottom. A hydrostatic dead end. To move it at all, the team had to break the suction and lift something that had been turned into a steel sieve. Standard patching and pumping would fail because the keel had been blown open where you couldn't even reach it. A plate over a bomb hole on an upper deck is straightforward. Sealing blast craters along a keel buried in mud is another world entirely. And that is exactly the step the surviving record never explains. Without the ability to lift the wreck as a single object, the engineers worked in a zone where one wrong move could shift thousands of tons without warning. Mud held the hull hostage. Torn bulkheads refused to trap air. The clearance demanded an aggressive approach that left little room for error, and almost no clean paper trail to explain how they did it. The historical blind spot is simple. We can see the result, but the method is mostly missing. Baltic Fleet engineers weren't trying to save a battleship. They were reopening a working harbor so supply traffic could move again. In that logic, the wreck wasn't a relic. It was an obstruction to be cleared off the chart. The scale of this specific obstacle was staggering. The sunken warship measured 418 feet 8 inches in overall length. That represents an immense continuous footprint of jagged, compromised steel burying itself deeper into the harbor mud every day. The engineers had to confront this continuous wall of metal using only the austere, improvised resources available between 1945 and 1946. The port infrastructure surrounding them was thoroughly devastated. There were no pristine, custom-built heavy salvage ships waiting offshore. They had to rely on sheer combat engineering, adapting whatever heavy cables, industrial pumps, and raw steel they could scavenge from the surrounding ruins. With the lower hull deliberately shattered, the usual refloating logic was upside down. The record never settles on what they used. External cofferdams built up from the exposed decks, heavy pontoons sunk alongside for lift, or some hybrid improvisation. Any pontoon plan would have forced divers to fight dense, freezing silt just to pass cables beneath the hull. An operation so volatile the wires could act like a garrote, cutting up through weakened bulkheads under extreme tension. Alternatively, if they attempted to patch the hull, it would have required an unprecedented volume of underwater welding on jagged, bomb-warped plates, followed by a continuous, overwhelming pump capacity designed to simply outpace the incoming floodwater. Whatever brutal mix of techniques they used, the fine-grained math is a ghost in the archives. What matters is the outcome. The hull broke free, the berth reopened, and the port went back to work. But lifting her out of the mud was only phase one. The resurrected dead weight still had to survive a deep water tow to wherever the Soviets could control it next. In the narrow maritime weather windows of 1946, moving a resurrected deadweight across the open ocean required a calculated gamble with physics. Lifting a shattered hull from the harbor floor was only the first phase of the engineering problem. The second phase was surviving a deep water transit. To accomplish this, the salvage teams had to master buoyancy restoration physics. This mechanical principle governs the physics of displacing internal floodwater with air. It demands the absolute sealing of hull breaches to maintain sufficient trapped air, which is the only way to overcome the massive dead weight of flooded steel. Under normal conditions, a ship relies on its original watertight compartments to provide this necessary volume of displacement. However, this specific vessel had suffered catastrophic internal explosive destruction. The lower decks were essentially gone. The rigid steel envelope required to trap air no longer existed along the bottom of the ship. Therefore, the engineers could not rely on passive buoyancy alone. Keeping the enormous mass afloat would have required extensive temporary sealing and aggressive dewatering. Heavy pumps may have been installed across the surviving upper decks to keep upper spaces as dry as possible while fighting constant inflow through the damaged bottom. A sustained pump failure could have been catastrophic. With the pumps screaming, the Soviet Salvage Command initiated the long tow across the Baltic Sea. The objective was the Copley shipyard located in Tallinn, Estonia. This transit fundamentally changed the nature of the salvage operation. Inside the protected harbor, the water was flat and predictable. The hydrostatic pressure acting against the temporary patches and the weakened bulkheads was constant. But once the tow crossed into the open waters of the Baltic, the dynamic forces of the ocean took control. Wave action introduces massive, fluctuating pressure spikes against a hull. Every time the crippled dreadnought pitched into a swell, the water pressure slamming against the forward temporary seals multiplied exponentially. The internal physics were even more dangerous. Thousands of tons of seawater still moved freely inside the hull, and every roll in the swell sent that weight surging from side to side, dragging the center of gravity with it. The men on the tow had to watch trim and list like a heartbeat, shifting suction lines and flow between spaces to keep the ruin from rolling past the point of no return. The towing vessels operating ahead of the dreadnought faced their own extreme constraints. The tugboat captains had to maintain an absolutely precise speed and heading. If they pulled too aggressively, the sheer hydrodynamic drag against the blunt, torn bow would rip the temporary steel and timber patches clean off the hull. The ocean would immediately rush in, overwhelming the pumps in seconds. Conversely, if the tugs moved too slowly, the massive towing cables would slacken. The unpowered dreadnought would lose its forward momentum and drift sideways into the troughs of the waves, exposing its broadside to the rolling swells and guaranteeing a rapid capsize. The transit to Estonia was a continuous crisis of tension and flow rates. The survival of the entire operation rested on the reliability of scavenged pumps and the strength of improvised welds holding back the Baltic Sea. Through sheer vigilance and mechanical endurance, the salvage team successfully navigated the weather window and maintained the precarious buoyancy. The shattered hull finally arrived in the sheltered waters of Tallinn. The deep water transit was complete, and the wreck was moored in the Copley shipyard. Here, it was reportedly used for a time as a stationary hulk, an accommodation or storage platform, while Soviet planners weighed what to do with the shattered ship. It appeared the ruined vessel had finally found a quiet, static resting place in the aftermath of a global conflict. However, the Estonian shipyard was merely a holding pen. The Soviet military command had already devised a final, violent purpose for the obsolete steel. The massive engineering effort required to resurrect and transport the ruined hull usually leads to one of two logical conclusions. A salvaged warship is either dragged into a dry dock for extensive repairs, or it is towed into a breaker yard to be cut down for scrap steel. But the Soviet military command flipped the decision entirely. The critical port restoration was long behind them. The harbor was functioning, and the dead weight had served its temporary purpose as a floating warehouse in Tallinn. By late 1947, into 1948, depending on the account, the Baltic fleet recognized a unique, brutal utility in the shattered vessel. Tugboats hauled the stripped hulk out toward the Gulf of Finland to the Neugren shallows near the island of Osmasar, where it was intentionally grounded and used as a realistic target for weapons testing. It was a deliberate grounding in very shallow water, shallow enough to keep the wreck visible and shallow enough that it could not simply disappear into depth. Executing a static live fire grounding requires precise navigation and timing. The towing vessels must build up sufficient forward momentum to drive thousands of tons of flooded deadweight high onto the submerged shelf. The tugs accelerated toward the designated shallows, holding their course until the last possible moment before releasing the massive steel towing cables. The immense ruptured keel slammed into the seabed, grinding through the coastal sand and gravel until the sheer friction finally overcame the mechanical inertia. The battleship wedged herself permanently into the earth. The bathymetry of the location was chosen perfectly. Because the water was exceedingly shallow, the battered superstructure and upper decks remained completely exposed above the surface, towering over the waves. This deliberate beaching created a massive, highly visible, and highly reflective steel mountain in the middle of the sea. For a military force rapidly advancing its technological capabilities, this was an invaluable training asset. If they had simply scuttled the ship in deep water, it would be gone forever. By leaving it hard aground, the hull could never sink, no matter how much new damage it sustained. It was the perfect, unkillable enemy. The Soviet Navy and Air Force immediately began utilizing the grounded hull as a live fire target ship. Starting in 1948, the remnants of the once mighty warship were subjected to a continuous punishing barrage. Squadrons of strike aircraft used the rusting silhouette to calibrate their bombing sights. Surface vessels tested their gunnery against the massive steel broadside. Year after year, the superstructure was hit, shattered, and melted by high explosives. The irony of this outcome was absolute and undeniable. The exact machine built and deployed to initiate a global war of conquest was now spending its final operational days being systematically pulverized by the very military force it had once actively opposed. This punishment continued into the 1960s, and the above-water remains were later dismantled in the early 1970s. By then, there was barely anything left to aim at, only a submerged hazard. But the more enduring threat wasn't the jagged steel, it was what remained inside it. The true hazard of this shallow water wreck site is no longer the jagged steel itself, but the volatile chemistry slowly degrading within its collapsed compartments. Over decades of military use, the physical structure of the dreadnought was obliterated, yet the most dangerous components of its history remain perfectly lethal today. This presents a modern risk shadow that fundamentally alters how maritime authorities interact with the coordinates. The site is now heavily defined by severe unexploded ordnance contamination. This specific marine hazard occurs when unfired main battery munitions and decades of unexploded air-drop bombs accumulate in a highly concentrated underwater area. As these explosive casings sit in salt water, the steel jackets corrode and thin out over time. The hazard does not fade on a predictable schedule. Fuses, detonators, and explosive fillings can remain dangerous for decades, and corrosion can make them harder to identify, more exposed, and potentially more unstable. When the Soviet military selected this location for a static live fire grounding, they transformed the surrounding seabed into a permanent catch basin for high explosives. Every aircraft bombing run and surface gunnery exercise that missed the central mass of the ship deposited live munitions directly into the silt. Countless heavy bombs struck the water at the wrong angle, failing to detonate on impact. They plunged into the freezing mud and vanished. Furthermore, the dreadnought herself arrived at this final destination carrying a lethal internal payload. Deep within her lower magazines, buried under thousands of tons of collapsed deck armor, lay her original 11-inch main battery shells. These massive projectiles were designed to punch through heavy naval armor. Each one contains a substantial explosive filler, typically tens of kilograms rather than hundreds of pounds, engineered to detonate on a slight delay after impact. Because the original salvage teams did not waste precious time extracting the deeply flooded magazines, the wreck arrived at the shallows with the unfired heavy shells still locked inside the lower handling rooms. When the superstructure was later hammered into oblivion by the continuous target practice, the thousands of tons of upper steel collapsed directly down onto those magazines, entombing the 11-inch rounds beneath an impenetrable, jagged reef. Today, this extreme concentration of original German ordnance and subsequent Soviet bombs creates an unapproachable exclusion zone. Modern authorities treat the area as hazardous, and prudent seamanship avoids anchoring, trawling, or any seabed disturbance in the vicinity of the wreck. The risk of a heavy anchor striking a degraded casing is mathematically unacceptable. A detonation from an 11-inch shell could be lethal at close range and could damage or sink a small vessel. It might also set off additional explosives under some conditions, but the scale and likelihood of any secondary detonations would be unpredictable. Environmental remediation of the wreck is currently considered an engineering impossibility. To clear the explosive hazard legacy, specialized diving teams would have to systematically dismantle the heavily mangled, collapsed steel of the hull to reach the lower magazines. Cutting into the metal using thermal lances or underwater chainsaws generates extreme heat and vibration, either of which would immediately trigger the crystallized explosives trapped in the mud right next to the cutting sites. Attempting to lift the scattered Soviet bombs from the surrounding sand is equally perilous. as the lifting slings could crush the thinned casings and initiate the detonators. The wreck has therefore been left to the slow, relentless friction of the ocean. Naval authorities focus on warning, charting, and risk management because corrosion changes the hazard over time rather than reliably eliminating it. Some munitions can remain dangerous for many decades, and the site may pose a risk for generations.